Good morning, students. Myself, Vaidegi, working as Assistant Professor in Sri Muthukumaran Institute of Technology. Today, the video lecture is from the subject ECC CEC 334 Analog IC Design. In this lecture, we will discuss compensation techniques used in two-stage operational amplifiers. We will study why compensation is necessary, understand Miller compensation and pole splitting, analyze the slewing phenomenon, and explore other compensation methods used to improve amplifier performance. The learning objectives are: at the end of this course, you should be able to explain the need for compensation in operational amplifiers, understand the working of Miller compensation, calculate slew rate, identify causes of slewing, and describe various compensation techniques used in modern amplifier design. First, we see about the introduction to frequency compensation. Practical operational amplifiers consist of multi-gain stages. Each stage introduces poles into the transfer function. These poles contribute phase lag. Excessive phase lag may cause oscillations and instability when feedback is applied. To prevent this problem, frequency compensation techniques are used. Compensation modifies the frequency response so that the amplifier remains stable under all operating conditions. Next, we see about the two-stage operational amplifiers. A typical two-stage operational amplifier contains a differential input stage followed by a high-gain voltage amplification stage. This configuration provides high gain and a good performance. However, because two stages introduce multiple poles, the amplifier may become unstable. Therefore, compensation becomes an essential part of the design. Next, we see about the compensation of two-stage operational amplifiers. The primary purpose of compensation is to improve stability. Compensation achieves this by shifting pole locations and increasing phase margin. A properly compensated amplifier produces stable output without oscillations. Among all compensation techniques, Miller compensation is the most widely used because of its simplicity and effectiveness. Next, we see about the Miller compensation. In Miller compensation, a capacitor called the compensation capacitor is connected between the input and output of the second stage gain. This capacitor introduces a dominant pole at a low frequency. The dominant pole controls the amplifier response and reduces the risk of instability. This technique is used in most integrated operational amplifiers. Next, we see about the pole splitting effect. An important effect of Miller compensation is pole splitting. One pole moves forward a low frequency and becomes the dominant pole. The second pole moves toward a much higher frequency. This increased separation between poles reduces phase lag at the unity gain frequency and improves phase margin. As a result, the amplifier becomes stable. Next, we see about the slewing in two-stage op-amps. Slewing occurs when the amplifier is required to respond to a rapidly changing input signal. The compensation capacitor can only charge or discharge at a limited rate because the available current is limited. Therefore, the output voltage cannot be changed instantaneously and follows the input at its maximum possible rate. This phenomenon is called slewing. Next, we see about the slew rate. The slew rate specifies how fast the output voltage can change. It is defined as the maximum rate of change of output voltage with respect to time. Slew rate is usually measured in volts per microsecond. Higher slew rate values indicate faster amplifier response and better performance for high frequency signals. Next, we see about the causes and effects of slewing. Slewing is mainly caused by the large input signals that require rapid output changes. Since the charging current for the compensation capacitor is limited, the output cannot respond instantly. This leads to signal distortion, slower settling time, and reduced bandwidth. Designers often increase bias currents or use advanced compensation methods to reduce slewing effects. Next, we see about the other compensation techniques. Besides Miller compensation, several other compensation methods are used. Lag compensation introduces a low frequency pole to improve stability. Lead compensation introduces a zero that improves transient response. Lead lag compensation combines the benefits of both methods and provides a balance between stability and speed. Next, we see about the feed-forward compensation. Feed-forward compensation creates an alternate signal path that bypass certain amplifier stages. This reduces phase lag and improves high-frequency response. The technique is commonly used in high-speed amplifiers where maintaining bandwidth and stability simultaneously is important. Let's summarize these topics. Two-stage operational amplifiers require compensation because multipoles can cause instability. Miller compensation is the most common technique and works through pole splitting. Slewing occurs when the output reaches its maximum rate of change. The slew rate determines amplifier speed. Additional compensation methods such as lead lag, and feed-forward compensation further improve amplifier performance. These concepts are essential in modern analog integrated circuit design. Hope you all understood. We will see in the next video. Thank you.